Today, my group and I will be discussing about integrated project for January 2021 semester 5. Our content should include the introduction, problem statement, and explanations for reaction engineering 1, process modeling and simulation, as well as separation process 2. Our group project team members include Siti Norsyamina Muhammad Saufi, Ester Revecca Robertson, Puteri Natrah Rizwan, and myself, Aloysius Victor Jubilee Underwood. Andy Bio is one of the leading biogas providers in Malaysia. As part of the company's major expansion plan to meet the increasing demand, the stakeholder is planning to build a new biogas plant with foam as the feedstock. In general, the plant design should consist of the following processes. Step 1, reaction to convert foam into biogas, and Step 2, downstream separation to increase the quality of the biogas. For reaction engineering 1, based on our research, this is the overall flow diagram for continuous tank reactor. And there should be two tank reactor, which is CSTR1 and CSTR2, where different processes occur simultaneously. Moving on, for CSTR1, there are two processes that will occur, which is hydrolysis and acidogenesis. And these reactions are represented by equation 1 as well as equation 2. For the hydrolysis reaction, hydrolysis involves the breakdown of carbohydrates, lipids, and proteins into smaller molecules of sugar, long-chain fatty acids, and amino acids respectively. This process is conducted by a group of hydrolytic bacteria such as Clostridium and Bacillus. Hydrolysis converts all raw material into amiable forms so that further microbial activities can occur. From hydrolysis, we proceed to the second reaction, which is acidogenesis. It is when hydrolyzed compounds are taken up by acidogenic bacteria such as Syntrophmonas, Pseudomonas, and Flavobacteria to form intermediary compounds such as alcohol, aldehydes, and volatile fatty acids such as butyric, propanoid, and acetic acids. Onwards is the reaction in CSTR2. Reactions involved are acetogenesis and methanogenesis, and these reactions are represented by equation 3 and equation 4. Starting with acetogenesis, products from CSTR1 are moved into the second reactor. The intermediaries undergo degradation to form acetate, carbon dioxide, and hydrogen, which are produced by acetogenic bacteria such as Desulfobrio and Clostridium. The last reaction process is methanogenesis. It is the final stage where it involves two different groups of bacteria, namely acetotrophic and hydrogenotrophic bacteria. Acetotrophic methanogens split acetate into methane and carbon dioxide, while hydrogenotrophic methanogens use hydrogen to form methane, all represented by an overall reaction formula.
Hi, I am Ester Revecca, and now I am going to present to you about our chosen reactor. A lot of experiment has been conducted by using different types of reactor in order to know which one is the best reactor to be used in treating the palm oil mill effluent. And based on our literature review, we have found that CSTR, or also known as the long-form continuous third tank reactor, is the common and the best reactor used in order to treat the palm oil mill effluent efficiently. CSTR is suitable to be used with a homogeneous liquid phase. This is because it is a steady-state system, and by saying steady-state system is that it is a continuous flow reactor where the reactants such as untreated palm oil mill effluent is continuously fed into the reactor, while the products are continuously produced as well, and the condition of the CSTR doesn't change with time. Next, let us move on to the advantages of using CSTR as our reactor. The first advantage is CSTR is simple to operate because it is also one of the common reactor used in the industry. Next is it has a lower operating cost and maintenance cost among all the reactors. And the third advantage is that it is suitable for wastewater with a high solid content, for example the palm oil mill effluent. And lastly, it is the most preferable reactor for the industrial scale, especially for the palm oil mill effluent treatment, as it provides a good contact between the wastewater and the microorganism through the mixing with the help of the stirrer. Next, throughout our literature review, we have found the optimum operating conditions for CSTR, which are the temperature of the feed is 70 degrees Celsius, while the temperature of the digester tank is 55 degrees Celsius. And the pressure of the tank is assumed to be 1 atm, while throughout our calculation we have found that the molar flow rate of the feed is 3424.7 dm/m³ per hour. And lastly, before we start the calculation, we have listed some of the assumptions for this system, which are isothermal system, steady state system, and also the density is constant throughout the process, which are 876 kg per m³, which is the density of the palm oil mill effluent. And lastly, throughout our calculation, we have found that there are 4 volume of reactors, but we have chose only the 2 highest volume, which is for the CSTR is 1311.40 m³, and for the volume for CSTR2 is 1322.29 m³. Thank you.
Hi, I'm Shamina. Next, I will explain about the content and tasks required by the process modeling and simulation subject. In this subject, first we are required to develop dynamic mathematical models for the reactor. The modeling equation is developed based on the 4 reactions occur in Aspen hysis, which are hydrolysis, acidogenesis, acetogenesis, and methanogenesis, in order to convert the POM into the biogas. We developed the overall mass balance for each reactors, which are CSTR1 and CSTR2. In CSTR1, there are 2 processes involved, which are hydrolysis and acidogenesis, while in CSTR2, there are processes of acetogenesis and methanogenesis. We also developed the component balance for each component. However, no energy balance is developed since the energy stream is not considered in Aspen hysis. Secondly, we are required to simulate the steady-state reaction process based on the parameters in the CEB 2043 subject. The parameters that we use from the reaction engineering 1 subject are: first, the inlet temperature is 70 degrees Celsius, the pressure is 1 atm, the mass flow rate is 3425 kg per hour, the volume for CSTR1 is 1311.50 m³. The volume for CSTR2 is 1322.29 m³, and the mole fraction of carbohydrates is 0.1182, and lastly, the mole fraction of water is 0.8818. This is the simulation diagram of the process conversion of the POM into the biogas. There are 2 reactors used, which are CSTR1 and CSTR2. Firstly, the cellulose and water will feed into the first reactor to produce glucose and hydrogen in the process of hydrolysis, and this glucose will convert into ethanol, carbon dioxide, and acetic acid in process of acidogenesis, and the outlet composition of the first reactor will feed into the second reactor, in which the process of acetogenesis and methanogenesis occur. In acetogenesis, the glucose will react with water to produce acetic acid and carbon dioxide, while ethanol will react with water to produce acetic acid. And lastly, the acetic acid will convert into the methane and carbon dioxide, and our desired product can be obtained in the vapor outlet of the CSTR2. Next, we are also required to validate the simulation by comparing the result from simulation and manual calculation. The deviation error is calculated using the formula value from hysis minus manual calculation over value from hysis times 100%. From the result that we obtain, there are deviation error occur in the simulation and manual calculation. This is because of the several reasons, which are: first, the value of k used in Aspen HYSYS is different with k in manual calculation. In our manual calculation, we choose the lowest k to be calculated as the lower, because of the lower or the rate constant, the lower the reaction time, and the reaction time will become faster, while in Aspen HYSYS, different k are used for different reactions. Second, the reaction mixture is assumed to be isothermal system, while the reaction in HYSYS is operated in non-isothermal reaction. The deviation error also occurs because of the density of POM used in manual calculation is 176 kg per meter cube, while the density of POM in HYSYS is 1096 kg per meter cube. And lastly, no volume expansion is assumed in our reaction mixture, while Aspen HYSYS consider the volume expansion of vapor phase product, which can lead to the deviation error to occur. Lastly, we are required to perform sensitivity analysis by discussing the effect of temperature, pressure and mass flow rate on the reactor performance. The reactor performance is observed based on the mole fraction of the methane at the vapor outlet of CSTR2, which is the methane production of this process. So for the first effect of temperature on reactor performance, from the graph we can see that if the temperature increase, the mole fraction of methane will decrease. The sudden increase and decrease of the temperature will affect the digestion performance, and the methane production is the highest when the temperature is in the range of thermophilic condition and start to decrease when the temperature is higher or lower the range, and the range of the temperature of thermophilic condition is between 50 degrees Celsius and 60 degrees Celsius. Next, we will look at the effect of pressure on the reactor performance. Based on the graph, we can see that if the pressure increases, the mole fraction of methane production will also increase. It shows that the efficiency of the reactor performance is higher when the inlet pressure increases. This is because when the inlet pressure increases, there will be more reactant particles for a given volume. So there will be more collision between the molecules, which will increase the reaction rate, thus the production of methane will also increase. Lastly, the effect of mass flow rate on the reactor performance. From the graph, we can see that if the mass flow rate increases, the mole fraction of methane will decrease. This shows that the efficiency of the reactor performance decreases under higher mass flow rate. The higher mass flow rate can reduce the retention time of the reaction, and also, other than that, when the mass flow rate increases, there will be a decrease in the microbial community, which might be detected because of the increase in acidity. Subsequently, it will cause inhibition to the methane production. That's all for the subject process modeling and simulation.
From the previous section, we know that biogas is produced from palm oil mill effluent. However, the biogas produced is in raw state, where it consists of undesired contaminants such as carbon dioxide, hydrogen, sulfide, and also water vapor. The desired component to achieve pure biogas is only methane. Thus, purification system consists of biogas cleaning, drying, and upgrading is important in order to remove these contaminants to produce pure biomethane. This is the overall process flow diagram of integrated separation techniques for biogas purification. Let's first take a look at the first separation technique, which is the removal of H2S by using absorption process. H2S is an acidic gas, which is why it is required to remove prior to other separation process. Firstly, the stream of raw biogas containing CH4, CO2, H2S, and H2O is being compressed to achieve the operating conditions of the absorption unit. It is then fed through the bottom tray of the absorption column, where in the column there will be absorbent used, which is amine solution. Amine solution in the absorption column will absorb the hydrogen sulfide, leaving the biogas stream with the composition of methane, carbon dioxide, and water. When the amine solution inside the column is already saturated, it is then being regenerated by using the boiler to heat the solvent and then to dissolve the acidic components, which is hydrogen sulfide. For the next process, which is the removal of water vapor, adsorption process is used. Stream from absorption unit just now containing methane, carbon dioxide and water entered the adsorption column containing silica gel. This is the figure showing silica gel. Silica gel in the absorption column will absorb the moisture from the stream. When the silica gel is saturated, the valve of the first column is closed and the column will undergo regeneration by supplying heat to the silica gel. Meanwhile, for the second column, the valve will be open and absorption process of biogas stream will be continued here. These two absorption columns work alternately with each other. Thus, leaving these units will be the stream containing methane and also carbon dioxide. The final separation technique is membrane separation process to remove carbon dioxide. From the adsorption units, biogas containing methane and carbon dioxide will enter the membrane. In the membrane, since the membrane material type chosen is 6-FDA-HAB polyamides, the selectivity of carbon dioxide over methane is high. Thus, carbon dioxide will permeate quicker than CH4. As you can see in the repeat stream, contains triangular and circular components which are carbon dioxide and methane. By selective separation, only carbon dioxide will be permeated through the membrane while CH4 will leave the system as the product. To conclude, we have achieved the objectives of all three courses. For Reaction Engineering 1, we have successfully proposed an optimum reactive system for POME conversion where two CSTRs were designed with the assumptions and the calculation of all operating conditions and also the reactions involved. For process modeling and simulation, mathematical models are developed and is used to do manual calculation and finally compared with the result of Aspen-Hasse simulation. Justifications were also made accordingly. Finally, for separation process 2, we have designed a purification system consists of three separation techniques, which are the absorption to remove H2S, adsorption to remove water vapor, and finally membrane separation to remove carbon dioxide to finally achieve the desired component, which is pure biomethane.